Okay, so in this lecture, we're going to derive the so-called Cauchy-Schwarz inequality for 3D Euclidean vectors, right? So in the final form, it will look like something completely obvious, but we will use a rather elegant, approach to get to this result. And the method we will see can be generalized to arbitrary, vectors from a linear vector space, right? So first we'll start with 3D vectors and use a very nice, elegant geometrical approach to obtain this result. Okay, so suppose you have some vector A, right, and you have some other vector B. Now the vector A is fixed, whereas the vector B, the direction of vector B is fixed, but it can be scaled. Let's say you have the freedom to stretch this vector B as much as you want, right? So you think of some alpha times the vector B. So now one can ask the question, if I were to form a linear combination between this vector A and some scaled vector B, these two are two completely arbitrary vectors. So in general, we assume that they are not null vectors because they will give you those kinds of conditions will give you some extreme limits of the problem. So for the moment, let's assume that these are non-null vectors, and well, I mean, you can also consider cases where the two of them are pointing along the same direction and so on, but those are particular cases that you will extract later on. So for the moment, let's think of a typical case, like I have given this diagram here. There is a vector A which is pointing in a certain direction. There is another vector B which I am going to scale with a factor alpha, and I'm going to consider a third vector C that I can construct with the help of these two vectors, and I can come up with a vector C which is A times A plus alpha times B. Now I ask the question, how would I choose alpha such that the resulting vector C is the smallest possible in magnitude? So you're going to get there's a whole locus of points that you can generate, or a whole set of vectors that can come about, because this alpha is it's a factor that can take all values, all real values, right? So geometrically, you see that if I want, what is A plus alpha B? It is this third vector. I have the third vector is going to be minimal if I can somehow ensure that this third vector is going to be perpendicular to the direction of B, right? So then you can, I'll have to keep B to be exactly at this length, so that the third vector is going to be perpendicular to B. If I can arrange this, then I'm going to get C to be the smallest possible, right? So let me write down this condition. If I want to find alpha such that this A plus alpha times B is going to be perpendicular to B. So how do I do this? I know how to do this now. I just take the dot product of A plus alpha B with B, and then I just put it equal to 0. And immediately this gives me alpha is equal to minus A dot B divided by B dot B. Right? If I can choose alpha to be this quantity, then I'm going to be able to get the smallest possible vector that I can form as a linear combination of A and B, right? Now, so here is the argument. So you find the smallest possible vector, and even the smallest possible vector, the magnitude of the smallest possible vector must be greater than or equal to 0, right? So this is true for any vector. So we are trying to get an inequality out of this, right? I mean, this is a standard approach, which is you find the smallest possible value of some set of objects, and if you can bound that, then you have a strong inequality which comes. So the smallest possible quantity among this entire set itself is going to be greater than or equal to 0, right? So we'll just simply invoke this, which is a fact, and then we will see that will give us a very interesting inequality, which is a famous inequality. So C So I have written C as A minus A dot B divided by B dot B times B, right? So in place of alpha, I have put this quantity that I have just worked out. And then this C dot C must be greater than or equal to 0. So let me compute C dot C, which is just A dot A minus, I have A dot B divided by B dot B times B dot A. So then I have another, when I multiply with this, I get A dot B the whole square divided by B dot B. I get 2 times of this. And then when I take the square of this, the final quantity, this, A dot B the whole square divided by B dot B the whole square times B dot B. So one of these B dot B's will cancel. And then again I will get back the same term. So I have a plus A dot B the whole square divided by B dot B. So if I, cancel out one of these terms from the second and the third, then I am just left with A dot A minus A dot B the whole square divided by B dot B. Now this quantity must be greater than or equal to 0. Right, so if I rearrange these terms, I have the famous Cauchy-Schwarz inequality, which states that if I take the inner product of any two vectors, square it, then this necessarily must be less than or equal to A dot A times B dot B. Right? This is the Cauchy-Schwarz inequality applied to the 3D vector case. But a little bit of thought reveals here, it seems like not at all a surprise, right? So one way to think of this is just use the cosine formula. We had this dot product of two vectors A and B can be written in terms of the cosine of the angle between the two vectors and the magnitudes, right? So then of course A dot B will just become the square of this is just A dot A times B dot B times cosine squared of theta, right? So all we are saying is that A dot A times B dot B times cosine squared is less than or equal to A dot A times B dot B, which is certainly true, right? Because cosine squared theta is going to be less than or equal to 1, right? This is how cosine works. And so in fact this is no surprise at all, right? But the power of this approach that we have just outlined is that it gives you a way to generalize this inequality. The Cauchy-Schwarz inequality is a beautiful and surprisingly powerful result, and it has applications in all kinds of contexts, and it has it can be generalized to other kinds of vectors, right? And this method we will see in the next lecture will carry through to arbitrary vectors in a linear vector space. Okay, that's all for this lecture. Thank you.